A recording for Tuesday, March 5th, and we just had a homework check for 6-1 and some homework work time. And now we're looking at 6-3, which is called vectors in the plane. And a number of years ago, I drew this picture, and I've just kind of always left it there. It's just an easy little reminder. So what a vector is something that tells us direction and distance. And so if we have these red vectors that you can see here, kind of going up and then across and then up and then down, then the resultant vector starts at the beginning of the beginning and goes to the end of the end, just to kind of let you know. And that's what we're going to look at in this one, and it's called vectors in the plane. Okay, so just give me a little head nod. Have you done vectors before? Okay, so we're going to use a mathematical approach for them, and I'm not sure if this is the same one, and so now we're going to look at vectors in the plane. So maybe weirdly some things happen there because somebody came in and asked me some questions. But now I'm ready to move on. So we're going to represent vectors as directed line segments. We're going to write the component form of a vector. And you don't have to write this now, but when we write the component form, I kind of think of it as, instead of like a parenthesis of like, you know, it almost looks like greater than and less than signs that it's between, but they're kind of the size of a parenthesis. And then we're going to perform basic vector operations, adding, subtracting, multiplying by a scalar, and represent them graphically. Write vectors as linear combinations of unit vectors. Find the direction angles of vectors. So that's why this is in this chapter, because we'll be making some triangles, finding, using not necessarily right triangle trig, but law of sines, law of cosines, things like that. And then use vectors, of course, to model and solve real life problems. So as an introduction, just quantities such as force and velocity. And I will tell you, I'm more of a math purist. I like to do math just for math. And these are kind of physics topics that we'll be dipping into, and very surface-like compared to maybe a physics class. And things such as force and velocity involve both magnitude and direction and cannot completely be characterized by a single number. And so this is a vector, excuse me, and our symbol for a vector is like, you know, back in geometry, this would be a ray, but a vector, we just kind of put one piece of that arrow at the top of it. And I'm also going to tell you that we'll see that in a minute, but when the book authors name a vector with a lowercase bold letter, there's no way for us to really kind of say this is a bold letter. So we'll continue to put this symbol for a vector. It has an initial point. It has a terminal point. The way you know the initial and terminal point is there's a dot at the initial point and there's an arrow at the terminal point as we go. And so this just kind of tells a little more about that magnitude and direction. The initial point, the terminal point always has that arrow at it. So these are directed line segments again, and the magnitude, you might want to, which is the length, and so you want to know that. The magnitude is listed as like this double bar, PQ for the vector, and then the double bar. So when you see that double bar, you're using the distance formula, or, you know, possibly the Pythagorean theorem would be appropriate, you know, if given a situation. So that's going to be using the distance formula. And if these directed line segments have the same magnitude and direction, they're equivalent, even if one is over there and one is over here. So they are still considered all equivalent as we look at that. So just some kind of background as we go through this. And I just seem to have like a couple things. So the vector v in the plane and the is denoted by a lowercase boldface letters such as U, V, and W. So this vector PQ, we can call it vector V, but since we can't show a bold, you know what I mean, and know that's always what we're showing when we're writing things, is we will still put the little vector over them. So vector U, vector V, and vector W. So we'll put that little arrow over it because we can't write the bold letters as we go. And then we'll show that U and V are equivalent on this picture. And you might want to graph this, and graphing it will help you kind of just have a sense of what's happening here. So I'm going to start by saying if we're going to show that these are equivalent, this is number one. And so vector U is the same as this vector PQ as we look at that. And vector V is the same as this vector RS. And I'm going to probably talk about them today as PQ and RS vectors. And so we need to see if they have the same magnitude and the same direction. So magnitude we just talked about. What am I going to use to figure out if they have the same magnitude? The distance formula. So the magnitude of PQ is going to be using the distance formula. So Cody, go ahead and put the distance formula in there with PQ and tell me what we get. Mm-hmm. Well, maybe I will write it. Yes, you're saying it. So x2 minus x1 in parentheses what? In parentheses squared. Okay, so there's our formula, and then go ahead and plug those in, even though some of them are zeros. Go ahead. And what do you get? And what do you get? Square root of 13. So PQ, the magnitude is the square root of 13. So we're expecting RS to be the same. So the magnitude of RS, Caitlin, go ahead and plug in things for me there. And what do I get from that? Oh, well, yes, 9. Yeah, 3 squared, which is 9, sorry. And that is, okay, and they said to show that they're equivalent, so that's what we want to do. So they have the same magnitude, right? So magnitudes are equal. And now, are we done? No. What do we have to do? Find the slope. So we have to show that they also have the same direction, and the way we're going to do that is we're going to show that they have the same slope. And so slope, how do you find slope? Isaac, just remind me of the formula first. Yeah, we don't use a lot of these things very often. Then PQ, vector PQ, we're going to find that slope first. Isaac, go ahead and put those numbers in. 2 minus 0 over 3 minus 0, which is 2/3. And then Danae help me with the slope of RS, vector RS, the slope of that. How am I going to do that? And that is 2 over 3. So their slopes are the same. Slopes are equal, so their direction, let me write that a little better. Their directions are the same. So pretty straightforward as we look at this. Now, just because we have this one on here, I'm going to talk a little bit about component form. It's in a slide or two here. But this one that's PQ is considered to be in standard form. Do you notice a difference? It starts at the origin and it goes out from there. And then do you also notice that 3 and 2 are maybe just a little more interesting points for finding that magnitude? The square root of 3 squared plus 2 squared is going to be the magnitude of either one. And then even slope, because these are zeros, the slope is going to be 2/3. So if it's in this standard form, that's kind of a nice thing. And we can put it then in component form. Component form means it starts at the origin and it goes out to whatever this point is. So the component form of U, we'll say, and let me use a different color maybe, I don't know, black. So, oops, I want to say that vector PQ is in standard form. Since we have one like that, we might as well say that. It's in standard form, and so what that means is it starts at the origin and ends at some coordinate point. Its initial point is at the origin, and that's what makes it be in standard form. And the initial point is at the origin, and that is 0, 0. And so I can put U, which is the same as vector PQ, I can put it in component form or write it in component form. And so I'm going to say U in component form is vector U is equal to 3, 2. And notice I'm not putting it in parentheses. So really, the component form of vector RS or vector V is also 3, 2. Do you agree? The component form of those vectors, if we would start either of them at the origin, we would always end up at 3, 2 as we go. And when we know that component form, we can start anywhere. For instance, this R1 starts at 1, 2. And if we add 3 there and add 2 there, we get 4, 2, which yes, it is 4, 4. 4, 4, which is that point S that we had over there. So if knowing that component form means we can find, other things that we're looking for. So this next section is called the component form of a vector. And so in this section, this beginning part of the section is a lot of just, here's our notations and the way that we're writing things. So component form of a vector is what we're going to kind of talk about, but that one was in standard form, so I think it was easy to talk about it as we go. So if the initial point is at the origin, and then it's considered the vector is in standard position, we already said that, and then that standard position from the initial point of the origin, and then the terminal point, if it's at V1, V2, then we can say the component form of vector V is V equals, vector v equals v1 comma v2. And you'll notice, we're just using u and v and w are very commonly used vector variables. Just like we use x and y, we use theta for angles and things like that. So then here is the component form of a vector. And because we're going to do some adding and subtracting, we have to define a zero vector. Well, just like the number zero is just zero, a zero vector, and this is a dark bold zero, so it means vector zero. It has the component form 0, 0. So its magnitude is 0, its direction is 0. So what should happen if I add the 0 vector to any other vector? Nothing, right? I just end up with that same vector. So here is the information you need to know about the component form of a vector. So the component form of a vector with an initial point P, which is, we're denoting P1, P2, and a terminal point Q, which is Q1, Q2. So vector PQ is equal to, and then components, so those kind of greater than and less than symbols, Q1 minus P1, comma, Q2 minus P2. So kind of the change in the x's and the change in the y's, and that gives us the component vector V1, V2. And of course, when we write that, we still write it with the little vector picture over it. So the magnitude or length, and notice what happens with the distance formula. The distance formula almost becomes the Pythagorean theorem, correct? Are you agreeing with that? So because you know that magnitude and direction, when we start someplace, and it can be anywhere, and we go this way, the change in x is going to be along here, and that'll be, if this is vector v, that's going to be v1, and then the change vertically, it would be v2, and you get that little right triangle. And so the magnitude is the square root of v1 squared plus v2 squared. And the next thing is a unit vector. It doesn't seem like a lot right now, but we will have to find unit vectors, and we'll use them quite a bit, because the unit vector just has a length of 1, and so it tells us that direction for sure as we go. So if the magnitude of v is 1, then v is a unit vector. And if the magnitude of v is 0, if and only if v is a 0 vector. And I don't have my little arrows over those, but I should as we look at it. So getting the idea of a component vector, form of a vector, and what we're going to kind of look at as we look at those. So here's two vectors. They're equal if and only if the first parts and the second parts are equal to each other. And that just runs you through. That shouldn't be earth-shattering news as we go. So the next one is find the component form and the magnitude of this vector v. So this is number 2, the initial point is 4, -7. The terminal point is -1, 5. And we have to find the component form and the magnitude of vector v. So first we'll find the component form. So that's vector v. And how are we finding the component form? Isaac, what are we going to do? No, well, that'll help us with the magnitude. We'll use the distance formula. But just how do we put these in component form? So I'll just back up a little bit, but make sure you're filing this away. So if you have the initial point P1, P2, and the terminal point Q1, Q2, it's just Q1 minus P1 and Q2 minus Q2 or P2, and the change in the x's and the change in the y's, okay? From terminal minus initial, as we look at that. So, related to slope, but not quite. Go ahead. What am I going to do? And so what is the component form of this vector? -5 and 12. So no matter where I start, if I go -5 and +12, I can get another terminal point as we look at that. And then the second thing is to find the magnitude of V. And the nice thing about the magnitude is once we have it in component form, remember, then we're kind of using that Pythagorean theorem. So Danae, how am I going to get the magnitude of this? So the square root of -5 squared plus 12 squared. And I left myself a little room because I was going to write magnitude. So to find that magnitude, and so Danae, what is -5 squared? 25 plus 144. What's that? Well, square root of 169. And then that magnitude turns out to just be plain old 13. And if it's not a regular number, we might have to put it in simple radical form. Everybody got magnitude and component form? And then our next thing is vector operations. And I'm going to leave you today with vector addition. And I want you just to look at this a minute, and then I'm going to put up the slide. So if this is the vector, half the vector is this. Do you notice that the vectors all have the same basic direction? What are you noticing about a couple of them? They go backwards. When do they go backwards? When it's negative, they go in the opposite direction, and then just multiplying by a scalar, which is that number out in front, determines the length of those vectors. This slide we'll talk about a little bit more tomorrow, but I am going to leave you with the definition of vector addition and scalar multiplication. And so we're going to use that parallelogram law. I'll let you write that, and then we'll look at those. Really on Thursday is when we'll look at that. And for those of you who are gone today, Professor Ouija is going to visit on Thursday, so we may not do it until next week. We'll see. So I will leave you with that problem or that information to write down, and then we'll talk about that next lesson.